Thank you, everyone. We can now start officially with the webinar. And on behalf of the topics webinar team and MDPI webinar team, I would like warmly to welcome you all today on today's event. My name is Mladen, and I will be your host for this session. And as many of you know, machine learning and remote sensing in general is transforming how we interpret the Earth observation data and enabling breakthroughs in the vegetation monitoring, ecosystem assessment, and sustainable land management, of course. And today, webinars brings together leading experts who will share their research, the recent advancements, practical applications, and so on. So before we begin, a quick note to all of you that the webinar is being recorded and will be made available afterwards. And you're welcome to submit your question at any time using the questions and answer feature on the Zoom. Before we officially start with the sessions, I would like to share the presentation about some general information about the journals that we are covering with this webinar, including also one special issue and different articles that are also relevant to the topic. So about MDPI, MDPI was founded in 1996. It is based in Basel, Switzerland, and today we have 450 different open access journals, and starting from some small journals and also some mega journals. And we are covering different topics, and our main goal is to enhance the open scientific exchange in all forms through all parts of the world. About the journals that are related to the webinar today, we will start with drones. This journal focus on some basics like design and application of drones, and including different kind of unmanned aircraft, vehicles, and systems. And we can say that this journal is one of the top journals in open access world when it comes to these topics. Also, remote sensing. Remote sensing is also one of our large journals with a big tradition. Also, of course, open access, and it covering basically every aspect of remote sensing science and applications. These are also some other journals that will be included today. Land, it is related to land system sciences, of course, urban studies, rural studies, land climate interactions, and so on and so on. And after that, International Journal of Geoinformation. I would like to highlight here that the journal is owned by International Society for Photogrammetry and Remote Sensing. And this is also one more important information about MPPI, that we also have collaboration with different societies, and some of those societies are also have related journals. In the end, geomatics, it's also open access journal related to geomatic sciences, and that journal will also be covered on today's webinars. This is the schedule for today's webinar. As you can see here, we will start with the chair introduction, Dr. Arnick Abdollahi, and after that we will start with the first speakers, Dr. Catherine, and after that we will follow this schedule. I would like to highlight that after each speaker, we will have like 5 to 10 minutes questions and answer session together with the discussion. And during the presentations, please feel free to ask questions in that question and answer box that we have on our Zoom platform. So I will make an introduction of our chairs at the beginning, a short introduction. After that, they will introduce all of the speakers for today. The relevant special issue is one that where our guest editors are actually our chairs, Dr. Arnick Abdollahi and Dr. Chandrama Sarker. It is titled investigating state-of-the-art machine learning approaches in vegetation analysis through Earth observation data. And as you can see here, the deadline for the submission is 25th May this year, but I would like also to highlight that we could extend that deadline, and the reason why we have this webinar is also to introduce people with these special issues. So we will probably work on deadline extension after everything is done after the webinar. These are also some relevant articles you can see here. I will not bother you so much with these. You can see all the information here, and those information will also be shared in the chat box during the webinar. So you can see two publications in Remote Sensing Journal here. And also we have some publications in Land Journal and in Drones Journal also. These two articles are published in geomatics journals and in the International Journal of Geoinformation. So altogether, there are 6 articles that we choose to show here because they reach a big number of views and citations, and that's why we are presenting those articles here. As I said, you will see this box here where you can ask questions. So please feel free to use it. And in the end, Dr. Arnick Abdollahi and Dr. Chandrama Sarker will be our chairs today. You can see that Dr. Arnick is coming from the University of Technology from Sydney, and Dr. Chandrama Sarker is an experimental scientist in Commonwealth Scientific and Industrial Research Organization. That's all from me. Dr. Arnick, please feel free to continue, and you can start with the introduction of the webinar. I will now stop sharing my screen.
First of all, thank you everyone for joining the webinar on investigating the state-of-the-art machine learning approach for vegetation analysis through Earth observation. My name is Arnick Abdollahi. I'm research fellow at University of Technology, Sydney, UTS, specialized in Earth and Space Science, Informatics, Artificial Intelligence, and Environmental Science. I completed my PhD at UTS, and then I was a postdoc at Australian National University, Bushfire Research Center. Then I was working on a big project on a national scale to enhance bushfire resilience through responsible use of AI in environmental monitoring through Earth observation, and then work on the wildfire fuel mapping across Australia. So now I'm also managing a leading different, again, national project that is how we can use AI-powered modeling approach for livestock farming to improve sustainability and productivity of livestock farm in face of climate change or even environmental issue like wildfire threats. So this webinar is about how we can utilize the applicability of the machine learning and Earth observation for vegetation mapping. And all of us know that the advent of Earth observation technology has transferred analyzing and monitoring of vegetation analysis because it can offer different types of data products at different spectral and spatial resolutions that can be used to analyze vegetation at different scales, from local to regional to national and even global scales, and then use that derived information for different applications like environmental aspects, wildfire, ecological aspects, agriculture application, biodiversity, ecosystem management, and everything. So in this webinar, but we all know that the Earth observation data and products comes at a high dimensional data set and very complex data set. So for that purpose, we need to have a very robust analytics method and sophisticated modeling approach to handle that kind of complexity of the data set and can derive useful and accurate information that can be used in different applications. So for that, in this webinar, you will see that we have great presentation from our great speakers that they will present how we can leverage the advantage of machine learning and Earth observation for vegetation mapping and use of that derived information in different applications. So this webinar, as Maiden mentioned, is sponsored and organized by a great team, a support team from MDPI, Remote Sensing Drone Lands, Geomatics, everyone. So that I really appreciate the support. So, and again, also thanks our speaker that they kindly accept our invitation to join and provide their insightful experience and research with us in this webinar. And also all the attendees I would like to thank for joining, and I hope that you see this webinar as much as insightful that you. So we will start with opening. We have the opening session speakers are the first that comes that will start with two speakers. I will be chairing the first session of the webinar, and then Dr. Chandrama Sarker will continue the next session of the webinar with another two set of speakers. So our first speaker is Dr. Catherine Ticehurst. She is a senior research scientist at CSIRO, received her PhD in geomatic engineering, and then she's working at CSIRO on landscape observation, mapping, monitoring a variety of vegetation and wetland environment using a range of remote sensing technology from satellite to airborne technologies. Research area include mapping surface water dynamic and regional scale, developing relationship between biophysical parameters of vegetation, time series analysis of monitoring crops, radar processing data, polarization, decomposition, and its relationship with mangrove and rainforest environment. Also have experience with working with high resolution imagery processing for crown delineation and using that for high biodiversity vegetation environment. Also experience with working with LiDAR data set to use that information into vegetation height mapping and that application in, for example, wildfire management and behavior modeling. So she's our first speaker that will be presenting on the topic on generating an Australia-wide vegetation height product by combining JEDI satellite LiDAR with optical radar and climate Earth observation data in a machine learning model. So we can start with Catherine, and if you please just mute your microphone, then we have like a less noise background, so we can hear our presentation as clear as it is. And over to you, Dr. Catherine. Thank you.
Okay, thank you for that introduction. So yes, like Dr. Arnick Abdollahi said, I'll talk about generating Australia-wide vegetation height product using a whole range of Earth observation data in a machine learning model. I want to acknowledge my co-authors, Rakesh Joshi and Sheza Hussain, who are also at the CSIRO with me. So this work is part of the National Bushfire Intelligence Capability for Australia. Up-to-date vegetation height provides important information for the Australian bushfire fuel classification, which can then be used to in-fire behaviour models. So the JEDI, the Global Ecosystem Dynamics Investigation satellite LiDAR instrument, was designed to measure vegetation height at a global scale. And it's been operating since 2019 on board the International Space Station, and it measures points on the ground at 25-metre footprints. So we need to combine it with spatially complete data to get Australia-wide vegetation height layer. So the JEDI data we're particularly interested in is the relative height, or the height at which the percentage of returned energy is reached relative to the ground. So in the example here, you might have a 25-metre footprint covering some forest, partially open forest, and we'll see a strong ground return and then some information throughout the canopy up to the top of the canopy. The JEDI uses the infrared wavelength, so it is affected by cloud cover, so the acquisitions can be quite irregular. when it acquires data, there's 8 parallel tracks with 25-metre footprints every 60 metres along the track, and these tracks are separated by 600 metres. So the JEDI data that I've been using was provided to me from Kimberly Opie, who downloaded all the data available from 2019 to 2023. That we're using the JEDI level 2A data. And then what she did is cleaned up the data using some of the standard quality flag information. But then we did a further filtering of the data to remove hopefully remaining outliers in the data. And what we did was use this other data set, another NASA data set, where they look at global vegetation height metrics with JEDI and ISAT2. We're just looking at the JEDI data, where they provide a raster data summarizing the different vegetation heights. And so the JEDI at 98th percentile is usually considered to be the top of the canopy. And we used a 200-metre raster data from this NASA product of average 98th percentile height of quality points in every 200-metre pixels. They also provide the number of JEDI points that are used to calculate this average value as well. So what we did was removed any single JEDI points that was greater than 10 metres from this average 98th percentile value, where there are at least more than 2 observations within the 200-metre pixel. It's worth mentioning here that we also had access to some other data used in our study. One was the Terrestrial Ecosystem Research Network, or TERN data, AusPlot data. Kimberly processed this up for us. And so that's all the blue points you can see scattered across Australia. And they're all 100 by 100 metre plots describing vegetation height in each of those plots. Some airborne LiDAR was also processed for us from Simon Walker. These were 1 metre or 5 metre pixels of maximum height. And we use this to produce a canopy height model. And those regions are shown in the red circles there. So to have an idea of how well the JEDI data was comparing to the field TERN AusPlot data, we plotted the average 98th percentile against the TERN AusPlots where there was overlap. The x-axis shows the field height data and the right axis shows the JEDI data. The orange points are where the TERN AusPlot data was reasonably homogeneous in height, so there wasn't a lot of variability. And you can see there's a fairly strong correlation between the two. What I did do though was look at some of those outliers, and I'll just see if I can get the laser pointer. So some of the outliers up in the top right, the JEDI height was saying about 22 metres, whereas the TERN AusPlot was around 12 metres. But if we look at the outline of this 200 by 200 metre JEDI raster, you can see there's some reasonably tall trees occurring up in the top of that box, whereas the blue point is showing the centre of the AusPlot, around 100 metres from there. And you can see the vegetation down there is shorter, so that wasn't too bad. If we look down in the right, there's the JEDI saying it's around 4 metre height. AusPlots are saying it's about 14 metre. And again, it seems to be a bit mostly due to an offset between where the JEDI raster data is lying with respect to the AusPlot data, which is occurring up the top here. Another outlier you see in the bottom left is where JEDI is showing the data is around 13 metres within this square. Now, most of this area looks to be sort of open lands, but there is some trees down in the southwest corner, so maybe this is why it's getting taller measurements. Whereas the AusPlot data is definitely occurring down here in this open lands. So we compared our clean JEDI data with the airborne data, and the box on the left shows our airborne LiDAR data, and the points there are showing the location of some of the JEDI measurements. So what we did was calculated a 30 by 30 metre square around those points and calculated the 90th percentile height of our canopy, airborne LiDAR canopy height model, and produced a scatter plot of the two to see how they compared. And there was a reasonable correlation between our JEDI measurements and our airborne LiDAR canopy height model. But the main thing you notice here is that the 98th percentile JEDI height stops around 2.5 metres And for the bushfire intelligence work, we're interested in knowing some of this lower vegetation height because it's important in estimating bushfire fuel loads. So what we did was compared our airborne LiDAR height with the best JEDI relative height percentiles. And you can see from about 2.5 meters upwards, the 98th percentile is probably a good representation of top of canopy. Whereas below 2.5 meters, you can see that the best JEDI relative height percentile gradually drops with the vegetation height. So really you need vegetation height to know which JEDI relative height percentile to use, which isn't going to work. So what we did was developed an empirical method using the relationship between the JEDI 98th percentile with airborne LiDAR and use this to just tweak our lower JEDI height values in our model. So the spatial data that we were using in our model is the Landsat annual products available through Digital Earth Australia. This included land cover, in particular life form and vegetation cover, surface reflectance. We also looked at fractional cover, which consisted of photosynthetic vegetation, non-photosynthetic vegetation, and bare ground or bare soil. We also included JAXA's ALOS PALSAR annual backscatter layer, mainly the cross-polarized HV band, because it's been shown to have a relationship to vegetation structure. We included latitude and longitude, a digital elevation model, the shuttle radar topography meter data set at 30 meter pixels, and also looked at the long-term average temperature and rainfall, as well as a new persistent cover layer, which has been published by Randall Donahue and Luigi Renzullo, where areas of forest tend to have a very high persistent value because they don't change much through time, whereas some of the other grasslands will change a lot throughout the year, so that will have a very low persistent cover value. This shows some of the scatter plots of the JEDI 98th percentile compared to some of these layers. So this top scatter plot is showing photosynthetic vegetation, fractional cover plotted against the JEDI 98th percentile. You can see there is a reasonable relationship with the JEDI as the height increases. The green, you can see the green reflectance drops off with height, although there is still quite a lot of scatter down in these low values. The pulsar backscatter increases quite nicely with the JEDI height. And the persistent cover also showed a reasonable increase as well with vegetation height, but there was quite a lot of scatter down around these low values as well. So what we did is to put all these remote sensing layers together. Then we selected the closest pixel value for every JEDI point, cleaned it up, removed any null data, and it left us with about 1.3 million points for building our model. So we tested a selection of machine learning models, but we needed to consider the speed and size of this model because we were working at 30 meter pixel size across the whole of Australia, which is a huge area to cover. So we tested the random forest regressor, the categorical boosting or CAT boost regressor, and the extreme gradient boosting or XG boost regressor. And these were tested against JEDI heights, which were removed from the model training. And we also validated the model against some airborne LiDAR canopy height model, and as well as those turn AusPlot data. We initially found the random forest regressor was very slow to run and a very large model. The accuracy it was giving us was fairly similar to CAT boost and XG boost. So we dropped the random forest regressor model and concentrated on the CAT boost and XG boost models. And our data had a very large class imbalance. You can see that this histogram on the left, we had a lot of low vegetation height and not a lot of tall vegetation. So we looked at two different methods to see if we could improve that class imbalance. One was about sample weights, where the weight of the small classes increased to make them more important. And the other one was generating synthetic samples. So we increased the number of samples above 3 meters. And it was based on the current sample distribution plus allowed for some Gaussian noise. And that's what that new distribution looked like once we produced it. So our weighted samples method didn't perform very well. Here's an example on the bottom left, a scatter plot of the airborne LiDAR against the model height result from XG boost using the original samples. And you see our root mean square error was about 5.5 meters. the R-squared was 0.63. But when we used our weighted samples in our model, the root mean square error increased and our R-squared went down. And also, if we looked at some of the low vegetation, so this up in the top right-hand side, you can see this area is mainly pasture and dryland cropping. It's showing quite tall vegetation where it should be sort of below 2 meters. So the weighted samples method didn't perform very well in our data. The synthetic samples method did improve on our results. This example on the bottom left shows cap boost using the original samples when compared to airborne LiDAR data. Our root mean square error was about 5.6 meters and an R-squared of 0.6. These results improved with our cap boost when we included the synthetic samples. So R-squared went up to 0.67. So we decided to use a synthetic sample method for testing further. And when we did some comparisons between the cap boost model and the XG boost model, we found XG boost performed a little bit better than cap boost. So we decided to keep it for as our final model. You can see here the top box is showing the cap boost results when compared to our JEDI test data, the airborne LiDAR, and the field data. And overall, especially for the JEDI data and the airborne LiDAR, the cap boost was performing better for root mean square error and R-squared. Field data was very similar, but because it was better overall, we decided to continue with cap boost model. So the cap boost model was able to handle the large data sets efficiently, and it was robust to missing data. It also works well on our tabular data. And so the box on the left-hand side is showing how our model performed compared to the JEDI data, the JEDI training data, validation data, and test data. The root mean square error increased slightly from the training to the validation and test data, and the R-squared went down slightly, so indicating maybe a slight overfitting, but it wasn't too bad. And then you can see here our root mean square error when compared to the airborne LiDAR was about 5.1 meter root mean square error and an R-squared of 0.7. And with the OSPLOT field data, it was root mean square error of about 4 meters, R-squared of 0.5. Up on the top right, we can see the most important features. The pulsar HV band was the most important band in this model, followed by the Landsat surface reflectance, shortwave infrared, band number 2. Then the green surface reflectance, and then the bare soil fractional cover layer, followed by the land cover lifeform layer. This lifeform layer separates your woody vegetation from your herbaceous vegetation, so it was obviously helping the model quite well. So this is a result of our Australia-wide vegetation height layer for 2019. So you can see there's high vegetation around the east coast, down the south in Tasmania, and then in southwest Australia. And we're also seeing a bit of vegetation height showing through central Australia. So these lower vegetation heights are important in the bushfire fuel estimation, as I mentioned before. So we had a bit of a look at some of these lower values. In the bottom left showing a scatter plot between airborne LiDAR and model heights below 15 meters. You can see there's still a lot of scattering, but the general trend is in the right direction. And if we look at our imagery, this area I'm showing with the laser is near in central Australia. And even though it's desert, you can still see there's scattered vegetation throughout. And so our model was tended to pick up quite a lot of this vegetation. And then if we look at areas where there's open pasture or dryland cropping, we're seeing it has a very low height value, and the clumps of trees are showing up in our model. So it wasn't performing too badly. For the bushfire fuel classification work, we want to divide our canopy height into canopy height classes, and these are the height values here in this legend. The left-hand side is showing the original canopy height layer that was used in the bushfire fuel classification work, and the reference down below is Rakesh's manuscript that describes this process. On the right-hand side is our new vegetation height layer broken up into those canopy height classes. And you can see there's a lot more detail showing throughout Central Australia. You can also see on the left-hand side, a lot of Central Australia is defined as having a height between 2 to 5 metres, whereas we know that around a lot of that area, the vegetation is lower. So overall, it's performing quite well. We wanted to do a comparison of our work with some other global vegetation height layers. So one of them is by Potapov, where he combines Landsat and JEDI data to produce vegetation height for 2019, and another one by Lang, who combines Sentinel-2 and JEDI data for vegetation height for 2020. Excuse me. And we compared these to some airborne LiDAR that was acquired around a similar time. And so we've seen the Potapov layer, so they've just stopped their height at 2.5 meters and everything's just master zero below that. But it also has quite a lot of scatter for those higher vegetation. The Lang's model performs really well for that tall vegetation. But as we get to the lower vegetation below 20 meters, we see there's quite a lot of scatter in the data. Our model, which is shown here in the bottom left compared to airborne LiDAR, I just converted all the heights to nearest meters, so it was equivalent looking graph to the others. It shows the height, scatter of height is much better for those lower heights, but we do see the taller vegetation, there's this saturation problem where the height, we don't get a lot of height sort of above 30 meters. So yeah, to summarize the work, we found the XGBoost method performed better than CapBoost. The results were validated against airborne LiDAR with reasonable root mean square errors and R squared, and compared to field plots as well. So a model works better for lower vegetation than the tall vegetation, and so current work is just seeing if we can try to improve those tall vegetation heights above 30 meters. And we're in the process of producing vegetation height layer for a whole of Australia. We've already got one for 2019 as a starting point, but these will be 30-meter pixels and they'll be done over multiple years from the recent years. So yeah, that's it from me. So thank you for listening. I want to just re-acknowledge my co-authors, Rakesh and Sheza, and also acknowledge work supported through InBeacon and Turn and Kimberly Opie and Simon Walker for their help with getting the data ready. Thank you.
Thank you so much, Catherine, for a great presentation. It was very nice to see this. I've seen that you were working with CSIRO at this topic like a few years ago, and nice to see that amazing results.
Thank you.
Now we have time for question. If anyone has any question, just please drop your question in the question and answer box, then we go through. Here we have one. I think Dr. Chandrama has already answered, but what is that RH100 means? Already Chandrama, I think, answered, but if you would like to go through.
Okay, yeah. So RH100 is the, excuse me, the relative, is the JEDI relative height of the 100th percentile. So that means the highest point it's getting. And usually, I mean, most publications don't use this RH100 to represent canopy height because you can include outliers as well. So they tend to use the 98th percentile or the 95th percentile to represent the top of canopy.
So we have one question here. And also, may I also ask a question? If this product is already also publicly available for the researcher, if you want to go through to that product or not yet?
It will be, yeah, as soon as it's available. Well, it'll be rolled out most likely through the CSIRO data access portal, but that'll be available, publicly available.
So if it currently we don't have too much. Okay, is part of Australia we have good coverage of LiDAR? How did the model was trained? Question from Fuad.
The model was trained using the JEDI data scattered across Australia. We're using airborne LiDAR data to validate our model. Yeah, so like I said, we're using the airborne LiDAR data up in Queensland and some around the ACT. We know there's some other airborne LiDAR data scattered throughout Australia, but some of it was quite old. So we didn't want to use too much that was old in case if the height had changed due to bushfire disturbance and stuff like that.
Okay. Another question from Grant. Has any work been done on training a computer vision ML model from satellite imagery for vegetation height?
I'm not that I'm aware of, but I'm not 100% sure about that. Yeah, I mean, there's some models use the sort of textual information in your imagery to help train. So you're looking at, you know, your canopy shadow and stuff like that, which I know that Lang included there in their model. Yeah, I don't know if that sort of helps answer your question.
Mm-hmm. So another question from Gopal. I have also tried to get Jedi LiDAR data from my project working using GE, but the fetching of the data is really big problem. Is it because of the data is not available in GE for free, and do we have to get the data commercially?
Jedi data is freely available. I'm not familiar if it's in Google Earth Engine. I usually go to the NASA Earth Data Search website to do a search. It is quite a lot of data. When I was originally doing it, I was sort of breaking it up into tiles and downloading it that way, which made it possible.
So as a last question for this session, but if you have any further question, then we can back at the end of the webinar to just please refer to which speaker you are asking the question. The question is from Jan. Is there any validation done using ground truth data besides LiDAR imagery?
It was the turn Ozplot field data was the other thing we were using to validate our data as well. But there's only 4 points scattered across Australia. So yes, we're using that and the recent airborne LiDAR that we had.
Right, thank you. Just now jump to another speaker, but if you have any question, please just drop in the question answer, and then we'll back at the end. Our next speaker is Dr. Sanjeev Kumar, Associate Professor from University of Sunshine Coast. Dr. Sanjeev Kumar is a PhD geophysical science from Australian National University, work as an Associate Professor at the University of Sunshine Coast. He uses geospatial analytics to conserve Earth's resources. His research interests include mapping wildfire fuel distribution, host-barren area, vegetation regrowth, and ecosystem monitoring, utilizing analysis of both field-based and remote sensing data. Also, he has a leading project funded by SMART SAT-CRC and Asia Pacific Network for Global Change Research, the Queensland Fire Department, and local council. The topic that he will be presenting for today is Earth observation data fusion for improved mapping of weeds in natural and plantation forests with machine learning approach. So Dr. Sanjeev, over to you. It's like about 20-25 minutes for presentation. Thank you. And after we have question session. All right, Dr. Sanjeev,
Yeah,
I think.
yes.
Oh, okay.
So hello, everyone. So today I'm going to talk about Earth observation data fusion for improved mapping of weeds in natural and plantation forest with machine learning approaches. So in my initial part of my talk, I will be talking more about data fusion, the basics of data fusion. And then in the end, I'm going to show you some examples from some of the completed projects and some of the projects on which we are working currently. So what is data fusion? A process of combining data from multiple sources to create a data set with more detailed information. And on the left-hand side, you can see a multispectral satellite image. And some of the high-resolution remote sensing images are often accompanied with panchromatic data. And we combine properties of both the images to get higher resolution image. And then we subsequently use it for further analysis. Now, when we perform data fusion, these are the condition. It should preserve all relevant information. It should eliminate any irrelevant information and noise, and all the artifact and inconsistencies in the fused image should be minimized. So altogether, we get much better image for with better spatial or temporal resolution in some cases. Now, these are some of the broad classifications of data fusion. Like one of the most common data fusion, which most of you should be aware of, is band sharpening, where we combine band data with multispectral data. But we also use this technique for fusing multispectral and hyperspectral data or multitemporal data. Like a very good example is your Landsat 7, which had some stripes. And often you will see people using multitemporal data to get rid of that stripes. Now, heterogeneous data fusion is also becoming very popular, especially fusion of hyperspectral and multispectral data with LiDAR data. And if you will look into the way these two data sets are collected, it is very different. So that's why we call it heterogeneous data fusion. And same thing with synthetic aperture radar and optical, visible, and near infrared images. So whenever we fuse them, they are coming from very heterogeneous sources. And now we are also getting some example of fusion of remote sensing data with some big geospatial data, like social media data or mobility data. So still this field is emerging, but this is going to have a huge potential, especially if we are trying to incorporate citizen science data with our image analysis. Now, this is one illustration which shows different types of data fusion. We have got various type of observation platform these days, and especially the drones and terrestrial scanners are becoming more and more affordable. And we get multimodal data, which are of different types, like hyperspectral, multispectral, LiDAR, SAR, or big data set. And we fuse them for further applications. Now, these are the broad classification of different methods which are used for data fusion. And pixel-based method are the most commonly used one, and they are implemented in most of the software packages which are used for image analysis. But at higher level, we have got object level data fusion, which is also referred as early fusion. And here we integrate feature vectors, which are obtained from multiple sensor sources to connect different modality. So it is not just the fusion of image, rather some of the secondary products, and then we fuse them. And then at the highest level, we have got decision level or late fusion, where we train different modalities separately, or we analyze different data types separately, and then we integrate them to get our output models. And you will find examples of hybrid fusion where we use combination of all these three methods. Now, these are some of the commonly used pixel-based data fusion method, and you will find most of them in image analysis software packages. Like, and broadly, they can be classified as color space transformation, and then based on principal component analysis. And in some cases, people consider these two very similar, because here we transform the color space from RGB to hue, saturation, and value. And in some case, we use chromaticity of a color coordinate system. And in some case, we normalize the color, especially with RGB drone. We normalize the color before band sharpening. And then we have got principal component based method for data fusion, where we often replace the band one of principal component, which has got highest information, maximum information, with high resolution bands like panchromatic band. And then we have got nearest neighbor diffuse method, which is classified as multi-resolution analysis. Now, this is what we do in object level fusion method, where object or feature level fusion, it goes to higher level. And it also incorporates some of the feature extraction methods like image segmentations. And it utilizes some additional characteristics apart from spectral information, like texture, shape, and together with spectral information. And then we have got decision level fusion. I have never used it, but this is what it looks like. And we go for some Bayesian model or Dempster-Sheffer method for fusing the data. So in summary, what we do, we go for higher level products, and then we fuse them when we go beyond pixel-based method for data fusion. Now I'm going to present some examples from some of the past project and some of the current project on which we are working. In the past, we worked on some of the plantation area, which are affected by weeds like blackberry. Like we see blackberry in supermarket, they're quite expensive, but in plantation area, they are real threat because they compete for nutrients, sunlight, and moisture. Plus, they also make plantation area very prone to wildfires. And in natural ecosystem, we have got lots of weeds. And one of the weeds, which is very prominent these days in Southeast Queensland, it is called cat's claw. It is vine. So currently, we are working on one project where we are mapping this weed in the natural area. And earlier, we worked on in some of the plantation area to map different weeds, including blackberry. Now, this is what we did in plantation area, and I'm giving you some example from the drone data that we collected, because when we use drone, we can use very basic data like red, green, and blue, a true color image. And plus, we also get digital surface model from which we can calculate canopy height model. So this is what we did. We collected drone data, then we created orthomosaic and point cloud. And then from it, we generated digital surface model and then canopy height model. And then we fused this canopy height model with RGB data set. So these are some of the things that we did. Like we used an algorithm called marker control watershed segmentation. So that is applied on canopy height model. And that create a segment of all the above ground vegetation. And we also, because we had in this project, we had limited spectral information in terms of red, green, and blue. So we derived all these indices. And then we create a single data set on which we further applied other analysis. So this is one example of end product that we generated from our study. And in this image, you can see some more example. Like this is a plantation area. It is a pine plantation. And in between the rows, this is an orthomosaic from drone. And in between these three, you can see lots of weeds. So this is the canopy height model. And this is the segmentation technique applied on canopy height model to create separate polygon for each tree. And in this study, what we did, we wanted to estimate all vegetation other than pine plantation. So we removed all the pine trees from the image for further analysis. So this is what we did. And these are some example of the product that we created from all the indices and from the canopy height model. And then we applied classification on this data set. So this is how our result looked like. So I think that slide is missing. So in this image on the right-hand side, you can see in between, you can see classification of weeds. And if we will remove this canopy height model using this approach, then this will give us a very good classification of the weeds and also their volume. So this is one project that we did. The other project on which we are currently working is in the natural area in the Gold Coast region. And this area is, like many other area, is affected by a vine which is called cat claw. And you can see it creeps on the ground, and also it climbs on the tree. So it is not so easy to map this weed because mostly it will be in the understory of the tree. But when it establishes itself, it climbs on the top of the tree and it covers everything. And it has got slightly different spectral behavior. Like this is one area which we are studying. And we collected a lot of ground data also. And whenever we collected ground data, we also took a photograph. And when you are taking photograph, you can always geotag your photo. So that also gives very good information for cross-checking. You can see the photograph taken from these locations, and then you can validate your results. Now, this is one of the pan-sharpened image that we generated. This is WorldView 3 data. So it has got 8 visible infrared, visible and near infrared band, and another 8 shortwave infrared bands. And if you will look at the riparian area, these are the area which are affected by the weed. So we applied some segmentation methods also, and then we are extracting the area which are affected by this cat claw weed. We are also going to use canopy height model derived from LiDAR, and that will help us in separating some of these area which are affected from some other area which are not affected. And this is another example of multi-temporal data fusion. So this is a location in Sunshine Coast, a national park which has been burned over time. And you can see these are Landsat archive from 1991 to 2013, and all part of this national park was burned. And we were investigating some of the underlying drainage pattern because this area is geologically very, very interesting. And you can see multi-temporal data is fused, and we can see entire soil, which is always covered by vegetation. So this is just another example of multi-temporal data fusion. So I will conclude by saying that with increased availability of data captured by different sensors, together with advance in methods as well as computation tool, data fusion is going to be the key because we are also going to involve some of the complementary data set. And this is always going to improve spatial resolution of remote sensing data, their classification accuracies, and also it is going to enhance object detection. So this is all from my side.
Thank you so much, Dr. Sanjeev. That's a great presentation and interesting topic of interest to research and to explore. So now we have time for question. If you have, just please drop your question in the question and answer session box, and then we'll go through to each. Sorry, Dr. Sanjeev, may I ask a question?
Yep, go ahead.
Is it multi-temporal data fusion? You mean considering the temporal dimension of the data, or is it spatial?
Yeah, so that is the temporal dimension. So here your spatial resolution won't change, but you can see some additional information. So it all depends on what you want to do. Because like a very good example is from Landsat 7. Because there was a time back in 2011 or 12, I think 11, 12, 13, sometime when Landsat 5 was stopped working and Landsat 8 was not launched. So we were left with Landsat 7, and Landsat 7 has got its stripes from 2001 onwards. but these stripes location will keep changing. So people often used to fuse these two data together to get a complete image. The other application of multi-temporal fusion is in getting cloud-free image. Like planet is very good example. If you will look into median image, that is another example of data fusion, and you can get rid of any cloud cover.
Yeah. So in this data fusion can be in one set of products or even multiple.
It can be in it can be what we call multimodal. So like traditionally, if you're looking into the conventional practice, it is all band sharpening sort of thing, and we use different algorithms for that. But now people are attempting to fuse multispectral with SAR data. And in some cases, they have provided information or some investigation about using some of the big geospatial data like social media and other things. So still, I will say it is in early phase, but that is also an option. So we are moving towards more diverse data fusion.
True. So we have one question from John. Can you share some documentation of article on data fusion?
Yeah. Yeah. Yeah, I can do that. Not right now, but yeah.
Okay. And question from Gopal. You mentioned advances in computational tools in conclusion. Are there any specific tools, platform, or libraries like G, Snap, or TensorFlow that are most promising for handling heterogeneous remote sensing data?
It all depends on what you want to do. Like Google Earth Engine, if you want to fuse temporal data, it is a very good tool. You can very easily create a median image to get rid of any cloud cover. And again, you can go for some of the statistical method, or you can go for any machine learning based method. So it all depends on what you want to do and with what sort of data you are working with.
Question from Debanjan. Can we use vision transformer in this case for image classification?
Yeah, there are some model which are retina based, so which is used in general image processing. So definitely you can use any model. And also resolution of the data have significant difference in resolution. So again, most of the time we try to improve resolution of the data through fusion. And the key challenges from optical SAR, LiDAR will be like the way these data sets are collected are very different. And sometime when we will fuse unprocessed data, we may not get anything. But like with LiDAR, suppose you have got high resolution image, and instead of panchromatic band, you can use canopy height model. So that also give us a lot of good result, because the spectral signature of vegetation on ground and on the top of the tree, as in our case, it might be the same, but you can easily differentiate between them if you are incorporating canopy height model. So again, you will have to find some way what is the best product that you can derive from particular data, and then whether you can fuse it with the other one or not. So that is going to be the major challenge.
So another question from Gopal. What are the key challenges faced when using data from optical SAR and LiDAR sources?
This is what I was saying, that you have to derive some of the product rather than fusing raw bands, because these data sets are collected very, very differently. SAR is backscatter, your optical is reflectance. So principally, if you are just fusing them raw, it is not very much recommended and you may not get anything. But if you're deriving some products out of them, and good example is canopy height model plus multispectral, then that is going to give you some very useful information.
Okay, perfect. Thank you. If we don't have any more question now, I have one more.
Yeah.
Question from Mohammed. Is multi-temporal data fusion across sensor can be useful in vegetation phonology related study, knowing the complexity of fusion alternation to temporal signature?
So again, you have to understand the area, because when you're talking about phenological information, that may change very fast. So if you're fusing any multi-temporal data, then you have to be aware of it. And again, like if I take example of this multi-temporal data set, we did it band by band. So like in some band for the bond area, so all the red area are bond area. And when the area is bond, you can see the pattern on the ground, which is not visible when it is covered by vegetation. So again, in this case, our purpose was to see the soil. So we use certain method to create this fusion. But if our purpose would have been to investigate vegetation, then we would have gone for something else. So again, when you're going for any such fusion, then you have to be aware of like phenology. So you have to be aware of all the properties for different seasons, and then you should be proceeding for any such fusion. So whenever you are going for any heterogeneous data fusion, be very careful. You should understand a property of the area you are studying and the sensor.
Thank you, Dr. Sanjeev. Now I just hand over the rest of the session to Dr. Chandrama Sarker for sharing the next part of the webinar. Thank you, everyone.
Welcome once again to the webinar. I'm just quickly sharing my screen. Can you see my screen?
Yes, everything looks fine.
Thanks everyone for joining today's webinar. Just a quick introduction for myself. I'm Chandrama Sarker, and I'm an experimental scientist at the Environmental Business Unit in CSIRO. Currently, I'm involved in two different projects in CSIRO. The first one is the National Bushfire Intelligence Capability, where I work as a remote sensing and GIS analyst. And the main work that we are doing in NBIC is preparing a nationally standardized data to understand Australia's bushfire hazard and how this will change with climate change. And the other project, the interesting project that I'm working with is the Telecommunications Resilience Investment Pilot Project, which explores how organizations in the telecommunications sector can collaborate to diagnose and understand their shared exposure and vulnerabilities to the bushfire and floods. We are actually using some of the end products of NBIC to the TRIP project. And also, my sincere thanks to MDPI Remote Sensing for collaborating to make this webinar happen. And I sincerely thanks to all our speakers for sharing their expertise and insights. So let's welcome to our next speaker. He has already introduced himself, so I'm not going to take much time. Dr. Arnick Abdollahi is a research fellow at the University of Technology, Sydney. He specializes in earth and spatial science informatics, artificial intelligence, and environmental science. He manages a national initiative developing an AI-powered grazing planner to support sustainable livestock farming in the face of climate variability and bushfire threats. And today he is presenting his research insights on harnessing earth observation technology and machine learning for national biomass assessment in Australia. So without further ado, let's welcome to our next speaker, Dr. Arnick Abdollahi.
So for today's presentation, I just chose one of the topics and project that I was been working on that. And that project was actually funded by Australian Research Data Commons, ARDC, with collaboration with different partners around Australia to see that how we can utilize Earth observation technology and machine learning for biomass estimation and assessment at the national scale of Australia. So just go through to objective, what was the objective of this study, and then what types of data and method I used, and they show some results on different data set that I applied and different times, and also what was the key finding that I actually achieved through this project. So, as you might know, there are a list of primary fuel attributes that influence fire behavior modeling. So, and having accurate information regarding those data sets is really important and essential to feed into the fire behavior models, and then model fire behavior and simulate the risk of the fire. So those fuels can be fuel moisture content, fuel type, biomass or fuel quantity, fuel arrangement, fuel size, chemical composition, height, and fuel cover. So creating aggregated and harmonized fuel data set over Australia or even any region in another country as well. So it would be very essential and important to feed that information into the fire behavior models, having up-to-date information to provide us with real-time information that we can model and simulate fire. So, and for that, I'm just in this study, I just focus on biomass estimation through observation and machine learning. So that's why the objective of this study is to investigate the combined use of high-resolution satellite emission like Sentinels with 10 to 20 meter spatial resolution, and also JEDI data that Dr. Catherine also mentioned these types of data for fuel height estimation. So to create comprehensive biomass maps for the region of interest, that is Australia, and also explore the capability of machine learning, how we can use advanced machine learning model for processing this complex set of data set, and then create accurate estimation of biomass in different times or at the larger scale area. So, and biomass is considering as a total mass of living and dead organic material present on the ground. So, and that, and then use that information for different applications. So why is important? So we can use that information for carbon sequestration or carbon cycle assessment, mitigating the climate change effect, and also assessing fuel availability for forest fire. Also, it helped to gauge the potential impact of wildfire and also environmental degradation, climate change, strategies for mitigation and preservation, and also can assist firefighter in decision-making for prescribed burn and fire spread assessment for those areas that we have high level of biomass or density or low. So, and this just shows our overall workflow of the work. So we have Earth observation and also AI-driven machine learning model that can be used to assess and map biomass for the Australia. A specific task that I follow in this study is to explore the capability of machine learning model for biomass estimation. So that's why I came across with experiment of different architecture, different machine learning model with different hyperparameters and technique to find the best configuration and the best model that can work with complex data like remote sensing and also larger scale as Australia scale. So, and also test the model performance across various fuel types. So for example, forest, shrublands, or grassland, how the model perform in biomass estimation in different fuel types. And also explore the integration of multiple data set and factor instead of just relying on one set of data set. This will help us to have the optimized set of data set, improved data set, and then see that how we can enhance the accuracy of the model. And that's, so in this case, I use optical SAR, and those parameters that I use comes from spectral bands, vegetation indices, topographic derived information, so and all feed into the model to improve the result and get accurate result for the biomass estimation. This is show the overall methodology that I've developed for this, like overall workflow. We have the remote sensing product that's I use different types of remote sensing, that is optical data. I use Sentinel, and then topographic data, and then SAR data that comes from Sentinel-1. And also we have independent variable, that is LiDAR data that comes from JEDI as a target that we want to predict. So I use optical, topographic, and SAR data as an input feature for the model, and then the target is biomass to estimate that comes from JEDI. So each of these data are at the first is pre-processed. For example, cloud masking or noise filtering for Sentinel-1 for SAR data, and then the data composited at different time interval, for example, monthly, bi-monthly, or seasonally, to see that how the model perform in different time frame and what would be the best temporal composite to get the accurate biomass estimation. And then for the Sentinel, I use different bands, spectral bands, and also calculate different vegetation indices that feed into the model. So based on playing with different types of bands and different spectral indices, I finally come across with this number of spectral bands and vegetation indices that shows the better performance to the model. And also for topographic, I use elevation and slope that definitely affect the vegetation cover and density in different elevation, if it is high or down, or it's low, or a slope is in east or west. So, and also for SAR data is the data composite is similar to the optical data. Then I use the polarimetric decomposition to get vertical or vertical horizontal backscatter of the SAR data, and then all of these information integrated and aggregated into the one input layers to feed into the model. So, and from the other side, we have the JEDI as a target. So those values also extracted and then feed into the model. The data is split into training and test, and then the model trained based on the test data, and the test set is used to assess the accuracy of the model. And here the table shows that we have, I use in total 22 input variables to the model. Based on playing with variety of input feature, I found that this 22 is showing the best performance. So, and our target, as I mentioned, is JEDI. So I'll just briefly explain what is JEDI. JEDI is the first spaceborne LiDAR data that provide 3D information of the vegetation structure or earth structure, make precise measurement of forest canopy height, vertical structure of the vegetation, and also surface elevation. It's provide like a footprint. As you can see that the direction of the data that is going through to the ground and then collect the data, it comes as a footprint. So the data has 3 lasers with 8 ground tracks. So, and 3 laser is like one full coverage, and one is coverage laser, and then other 2 is full power that provide full canopy information. So has 60-meter long track and then 600-meter cross track. So, and each footprint comes with 25-meter spatial resolution that is somehow is matched with the Sentinel spatial resolution that is 10 to 20. And this show the JEDI products for biomass across Australia. So for the biomass, we have 2 types of data that comes from JEDI. One is level 4B and what is for 4A. The 4B is gridded data, that is 1 by 1 kilometer estimate of biomass estimation, that is from 2019 to 2023. And then the footprint biomass product convert each high quality waveform to a biomass prediction, and it's like a gridded, and you can see how it looks. But the JEDI level 4A is a footprint that comes with 25-meter spatial resolution, and it's reported that till now we have data till 2024. So as I mentioned, the gridded data has 1 by 1 kilometer grid cell, but the JEDI level 4A is like 25-meter footprint. So, and this is just example of the data that I downloaded based on different months. For example, January, you can see that how the JEDI level 4A, that is footprint, looks like. So you can see that how the data is actually coming from different direction. So, and so we have data almost, we have data for covering the full area of the interest, but we have the gaps in between. So to fill that gaps, that's why I use the other set of data remote sensing products like Sentinel to extrapolate, to train the data, the model based on this, and then extrapolate based on Sentinel to the whole Australia. So, and the data, you can see that how it looks. So each month has different granule, and it's the data comes, this types of data is really big data set. So it's pre-processing and processing of the data is super challenging. So it takes a lot of time to prepare and provide a clean set of data set. And also this is a statistical analysis of the data mean, max, mean, standard deviation for different months. So that's why I use each month of this data to train the model and then create monthly or bi-monthly or seasonally set of biomass estimation over Australia. So for machine learning, also we know that there are different types of machine learning, from basic machine learning models to the advanced machine learning models. So like traditional machine learning, random forest, support vector machine, k-nearest, to advanced machine learning model, neural network, or even deep learning models. So, but developing and choosing the model that is considering the trade-off between the accuracy and the speed when you're working with complex set of data set like remote sensing for larger scale area, that's the key point. So because, for example, if you want to develop a deep learning model with millions of parameters, then it definitely would be a very complex process. So, but it is important to how come across with the model that is fast and also can get acceptable result for the goal. So that's why in this case, I try to develop an ensemble model that comes from random forest and gradient boosting. These two are tree-based model that create the different trees based on different, for example, random forests split the trees in parallel, but gradient boosting is sequential, and then try to improve the previous trees. So, and for doing that, I consider the k-fold training steps. The models train at 5K, and then each model, and then we have validation for that is to how to validate. So in each repeat, the model repeat and then get prediction, and at the end ensemble to get the average of the prediction, and then validation is used to get the assessment of the model and check the final prediction. So after developing the model, see here just show the training data set that I prepared for the model. For example, the data that comes from the JEDI level 4B, because it was gridded and it was fully covered the area. So you can see that when you generate the training set, you would have the samples from the like all areas, and it's like a full cover. But for the JEDI level 4A, because it's only you have the data from those granules that is available and the data collected, then the training set is only for those. So, and I wanted to see that, and this is the attribute table actually that used for the model to train. So we have the location and also biomass, and then different land cover and filter, and also the information that comes from Sentinel mission. So I just try to use these two types of set, because one is gridded and one is footprint, to see that how the model perform in different set of data. And this is just show the results, monthly model performance and biomass estimation. So, and you can see how the model looks like. The model shows the promising results for different months. Although we have some months that the model performance a bit lower, and that's because when you composite the data, for example, Sentinel or SAR at the monthly level, so you may have not available data for the whole Australia. Maybe it's you have some part of the Australia that you don't have data, or you have cloud cover or something. That's why that affect the model performance. But as long as we have a good quality data set, even per month, then you can see that the model achieve good accuracy and acceptable performance for monthly mapping of the biomass. To check that performance even better, I try to consider different time frame analysis, like a bi-monthly and even seasonally, 3 months composite of the data. So, and for that, even the model performance improved, because when you combine like a longer time series, like a bi-monthly or seasonally, then you would have like a good quality set of the data set, and then also better representation of the vegetation during the season or even during the bi-monthly. So that's why the model performance shows better compared to the monthly. And based on the JEDA level 4A and B, we can see that the B shows the better performance compared to even the accuracy is more than 70%. So for JEDA level 4A is like 60% more than. So, and it shows that level 4B show better performance, and it was almost obvious because we have a spread of the training set over the Australia, and it's and that data prepared as based on the average biomass estimation, but the footprint data set that we have comes with different noises or outliers. Although I try to remove that outliers and try to apply a new method to remove that outlier in some extent and then check, but still there might be some others. So that's why the gridded data set show better performance in this case. So this is also show the seasonal mapping, spatial mapping of the model of the biomass for the Australia, and you can see that how it looks in different seasons. So, and as you can see, we have high biomass estimation at the east part, and then also down to the Victoria and Tasmania. So, and you can see the spatial distribution of the biomass for JEDI level 4A and B, and also in the middle that we have like a grassland or spinifex that has lower biomass density in these areas. So to do more analysis, then I consider applying the model and considering the estimation of biomass in different fuel types. For that, we have the Australian fire danger system that comes with 8 important fuel types, and for each fuel type, there is a fire behavior model. So for example, forest or grassland, spinifex, shrublands. And you can see that most of the area in Australia are covered by grassland, spinifex, and woodlands. So, and you can see in the table that the area of each fuel type that we have. So most area is covered by these 3 types of fuel type. So, and then I try to see that how the model shows performance and how the density of the biomass looks like in different fuel types. So, and you can see that based on the statistical analysis, we can see that the model shows highest result for example, forest and pine shrublands, but there is a little bit drops in grassland as in a spinifex estimation of the biomass, and that's because this area has a large coverage and cover the full area, the most area of the Australia, and also it's very sparse, and the variability of the biomass in these 2 types of the fuel types is very less. So that's why the model cannot capture that variability too much, and there might be some outlier that actually affect the model performance. So, but and then maybe just increasing the number of samples in these two types of the fuel type could help to improve the results, and also checking the outlier and removing as much as we can. So maybe that could help to improve the result. But generally, you can see that even the model shows the a promising result in different fuel types as well. So the key takeaway that I found here is that machine learning models have showcased proficiency in estimating biomass through remote sensing data at a larger scale area of Australia, and then combining the different set of remote sensing data, optical or SAR, can enhance the biomass estimation, yet further exploration can be also necessary or important. For example, those are data that comes with L and P bands. So JEDI data availability, offering LiDAR-based measurement of vegetation height, and has paved the way for biomass research in larger area. Further research can be used and do to retrieve other fuel attributes, for example, height, and then include and feed that information that comes from height into this model to even improve the biomass estimation. So having accurate and fine scale up-to-date fuel maps would be highly beneficial for precise map modeling or an investigation of biomass estimation across various fuel type, because the current fuel type map that I have is, I think, 2 kilometer spatial resolution compared to the 20-meter spatial resolution map that I created from Sentinel is too much difference. So that's why it shows the difference accuracy in different fuel types. So having accurate maps would be definitely beneficial in this case. As also, recent and accurate biomass validation data can be essential for verifying the outcome of the model, and the proposed framework enables us to generate harmonized and national scale biomass data set that can inform carbon cycle assessment and wildfire fuel management strategies. So this workflow is ready and can be applied to the different types of the another set of the remote sensing data to create biomass estimation at different years. Thank you so much for listening.
Thank you so much, Dr. Arnick. That's a very interesting presentation. Any question? There is one question from Pesto. Thank you for the insightful presentation. My question, did you evaluate the performance of different models? If so, what was the best model from your experience? Under which cover class does the model perform better? Dry areas, forested, agriculture, grassland, etc. How did you deal with different resolutions data? Did it affect the result?
So for the model, actually, I tried different model for the machine learning model. Like I applied, for example, random forest or XGBoost or any other types of model separately, and then try to check the performance of the model. And then at the end, I come across with this ensemble model that shows the promising results. But in terms of the differences between spatial resolution with the fuel type data that we have with app that I created, that is like a 20-meter spatial resolution from Sentinel. So this actually was the only data set was available to us to do the analysis. CSIRO actually was trying to update that map with higher spatial resolution, and so the goal is to check if that higher spatial resolution field type map could help to even better check the performance of the model, and even check that how the model could improve the result in different field types. So, but at that time, this was the only map that was available that I did the analysis.
Thanks, Arnick. There are a few questions also. Question from Rakesh Joshi. Hi, Abdullahi. Thanks for the great presentation. Do AGB includes liter biomass? And do you have any idea what is the ratio between AGB and BGB for different fuel types?
This is actually the above ground biomass, and I didn't consider the below, so that's why I'm not sure what is the ratio between that. But this is actually the derived information that comes from JEDI. So, and it's like a total biomass. Maybe it's like a considering the liter biomass as well or not, because it's like a derived information that comes from JEDI and is considered as a total. So, not sure. Sorry for that.
Thanks, Arnick. The next question is from Yan Cheng. Are the fuel and AGB database publicly accessible?
One set of this data is available in TERN, so that can be available to anyone. Maybe I can share later. And the new data set also is going through to publish soon.
Thanks, Arnick. Is there any other question from anyone? I have a quick question for you. So when you're using ALOS data, that is, I think 30 meter in resolution for the topographic elevation and slope.
Yes.
So is there any reason why you choose ALOS data for topographic elevation and slope estimation?
Actually, ALOS it comes with DSM that provide a more detailed information on vegetation compared to only considering the DEM. So that's why I use that types of data. And that shows better results compared to, because I use another set of data. I don't know what is that. But these types of data, when I use it, it comes with better result to the model.
Okay, thanks, Arnick. There is another quick question from Rakesh. Do you know any other database to validate AGB? I mean, ground survey data?
TERN has set of data, ground-based data set for validation. At that time I was working, so there was some set of data set, although the data was not too much up to date, like to cover the recent years. But if you want to have like a set of good data set for, like, especially for the previous years from 2010 or 15 onwards, then that could be helpful for you, maybe.
Thanks, Arnick. Thank you very much for your very informative presentation. If there is no, okay, there is another quick question from Pester for you. Out of all the parameters considered, which was more influential in determining AGBM?
I forgot to add this information, but I remember that vegetation indices show better. That was because based on the feature importance analysis of the tree-based model. But one important thing is to consider that feature importance analysis of tree-based model is not too much insightful to rely on, because the model actually when there is high correlation between the feature, that types of analysis does not consider, and it's giving you a wrong kind of information, so it's not helpful too much. So, but based on that simple analysis, I figured out that vegetation indices from Sentinel was the highest.
Okay. Rakesh has put forth another question connecting to his previous one. He asked, but do we have access to data to 2015 onwards? In turn, I think he mentioned.
In turn is available, and also I remember that I downloaded some set of the data. Actually, they shared some set of data set to me. I need to check and then back to you, Rakesh. No worries.
Yeah, he's asking for the ground truth data. Question from Yan. What are the accuracy assessment for the AGB result? Sorry if I missed out the information from the presentation.
I think the presentation also would be shared, if I'm not mistaken, but there are different accuracy assessment that I did for different composite set of the data set monthly or bi-monthly or seasonally. So that's why there is a different set of assessment.
Okay, thanks, Arnick. I think that's all for your question to you.
Thank you.
I'm gonna share my screen quickly to introduce our next speaker. So our next speakers are from CSIRO, Dr. Kate Giljohann and Dr. Roozbeh Valavi. Dr. Kate is an ecologist and ecological modeler at CSIRO, specializing in research to support environmental decision-making. She has conducted extensive research on fire ecology across southern Australia, including the development and testing of biodiversity resilience metrics and the coupling of biodiversity models with mechanistic fire regime simulations and scenario analysis to explore options for sustaining biodiversity. Dr. Roozbeh Valavi is a senior research scientist at CSIRO, specializing in spatial ecology and biodiversity modeling. He develops scalable scientific software for environmental applications, focusing on species distribution modeling and habitat mapping. He has extensive expertise in ecological modeling, geospatial analysis, machine learning, and scientific software development. Today, they are presenting collaboratively about their insights on ecosystem condition modeling using the Habitat Condition Assessment System, HCAS, and its applications in Australia. So over to you, Dr. Crate and Dr. Roozbeh Valavi.
Thank you so much, Dr. Chandrama. Let me share a screen. Hi, everyone. Thank you so much for joining the webinar. Today, I'm going to talk about Habitat Condition Assessment System. But before starting, I would like to begin by acknowledging the Bunurong people as the traditional owners of the land that I'm working on, and pay my respect to their elders past and present. So Habitat Condition Assessment, or HCAS, is a remote sensing-based monitoring approach that allows us to assess habitat condition in a nationally consistent way at a site level. Essentially, HCAS estimates the degree of departure of ecosystems from their natural state. The map that you can see, it's one of our products, is the previous one indeed. That is the long-term habitat condition over Australia from 1988 to 2022. But essentially, HCAS estimate condition by comparing observed versus predicted ecosystem characteristics derived from remote sensing data. Previously, we used MODIS satellite product for this, but now we have transitioned to Landsat imagery that allows us to work at finer spatial resolution and also include data from 1988 all the way through to 2024. As you know, MODIS was started from 2001, so there was no data prior to 2000. The result of HCAS is a robust data-driven framework for monitoring ecosystem across landscape using the best available satellite and environmental data. In HCAS, we use, as I said, remote sensing-based variables, environmental and climatic variables, and also reference ecosystem data. I'm not going to go to the details in this slide. I'll show in the next slide what we are using. In the latest version of HCAS, we are using 14 remote sensing variables to represent key ecosystem characteristics. These variables are generated based on summarized time series data, specifically through indices derived from what is known as geomedians. Geomedians is based on geometric median that combines satellite measurement collected over times over a specific time frame, for example, a year or 10 years, to produce one representative multi-spectra measurement for every pixel. And the variation of these geomedians with their individual measurement are also named geomads, which is median absolute deviation. There are 3 that we also included. We also incorporated fractional cover variables that including photosynthetic and non-photosynthetic vegetation and bare soil into the mix. Together, these variables give us a reliable, nuanced picture of ecosystem condition over time. And for the reference sites that I mentioned, reference sites are carefully selected site representing high ecosystem integrity to define a baseline for condition assessment. These sites are the location in Australia that we find they are in the most intact state of their ecosystem and are selected based on multiple line of evidence, including the expert knowledge, land use data, nighttime data, roads, and different source of maps. This graph that you see here is a very simplified version of the process that my colleague Dr. Giljohann has developed for defining these reference ecosystem sites. The HCAS or the HCAS system has 4 main components. The first one being the reference ecosystem modeling, or REM. What it is essentially we are using supervised learning methods to predict those remote sensing indices across Australia and use that to compare with the observed one. So these predicted versus the observed remote sensing variables gives us an indication of the departure from the expected ecosystem condition. In one of the steps, we also calculated probability surface, which is the likelihood of being in a reference condition based on the reference sites that I showed you. And all of these calculations are done in the multivariate distance space. So it's a multivariate space, distances in the multivariate space of these variables that I showed. And in the next step, we do calculate and compare every single pixel over Australia, which is around 1 billion pixel over Australia, with these probability surface to calculate the condition. And at the very end, we calibrate the result to present HCAS as an index between 0 and 1. And the first step that we calculate the reference ecosystem site, I just want to explain how it works because it shows how much the intensity of work and how much work is done in background to calculate HCAS. In this step, we start with the reference sites. So imagine these are few reference sites across Australia, but we have 500,000, not just a few. We compute all the pairwise distances between the sites with respect to predicted and remote sensing variables. And then these observed versus remote sense observed versus predicted distances, then they're aggregated to number of beans to compute the density surface that you can see in the lower corner. These later would act as a probability surface to evaluate condition of any new location. Before going to the assessment of every pixel, we normalize this probability surface with respect to environmental distance or essentially the predicted remote sensing distance. And this is because at any predicted remote sensing distance, we want to see relatively what we expect in the observed remote sensing as well. And for a single pixel, when we want to evaluate it, for example, for that patch of forest in the middle of agriculture areas, we first select the samples from the reference sites close by and calculate all the pairwise distances with the predicted and observed remote sensing, and filter those that are more relevant, essentially filter those that are closer in predicted distance, or they are environmentally more similar, because the predicted remote sensing distance is the prediction of remote sensing variables based on 46 different environmental and climatic variables. So it kind of have the impact and effect of environment. And those few last one that we select, we use that for condition assessment. Similarly, for a point in that agricultural land, for example, which is a modified site, it's not in its natural ecosystem. Oh, so we do the same, but the departure with what we expect to see in the observed remote sensing, it can help us to estimate the condition of that pixel. But moving to Landsat, definitely has improved the resolution, but introduced some challenges as well. For example, having the lower revisit rate of Landsat and frequent cloud cover mean that we needed to move to a 3-year rolling average instead of yearly data to be able to ensure data consistency over Australia. As you can see in this picture of Tasmania in Australia, it's a very cloudy area, and there is a rare occasion that you can find one Landsat scene without any cloud. So at the finer going to finer scale and finer resolution also demands more and better distribution of reference samples, and also having better environmental variables to cover that environmental variability in the landscape. On top of that, also moving to Landsat means that we used much larger data set and additional variables and also additional samples. We needed to also automate our workflow with high performance software to be able to analyze this data. This is one example that comparing on the left is the MODIS-based Landsat, which is the last version that we produced with that. That data set was the version 2.3 of HCAS, if you have been familiar with the HCAS series. And you can see in the middle is the HCAS version 3.1 that we produced last year. It is a Landsat based but aggregated to 90 meter. If you compare it with the RGB image on the right, you can see even the border of the fields that they have some vegetation cover also highlighted here. So you can see much more detail and much more accurate representation of the condition you can see in the new product of HCAS with Landsat-based product. This is also an example, like 3 examples from the mine sites in Western Australia. As you can see, the representation of these mine sites and the condition, which is the lowered condition, are very well captured in Landsat-based HCAS. But in MODIS, it was okay, but it couldn't very easily delineate between the mine site and the surrounding area. But in Landsat, it perfectly capture those variabilities in the landscape that are degraded, definitely. We also do parameter tuning and evaluation using land use data, especially this is a process land use data. It's not just the raw land use data. And based on the expert knowledge, we have some idea of how the condition or what is the expected condition in that land use, like that land use class. But essentially that land use class has a one value that we know that, okay, this is a one value from the reference site, for example. We have some idea, but we don't know the variation of the landscape condition within that land use, but we calculate that by HCAS. So we are using a sequential AUC to be able to maximize the discrimination between the land use classes and the HCAS scores, and be able to select appropriate parameters for HCAS that maximizes this AUC or area under the curve. We also have interactive diagnostic tools for checking the condition, how the condition is estimated, and how the model behaves with different parameters. For example, recently we introduced a penalty for having selecting samples that are geographically distant from the target point. And this is one of the tools that we are using to see the impact of that, like distant geographic distance penalty on the estimated condition, and testing the parameters. these are some summaries of the difference between the version 2 HCAS and version 3 HCAS. I'm not going to go through to the details. There are way more details that I covered here, but I need to finish my presentation and leave the rest of the presentation to my colleague, Dr. Kate Giljohann. Thank you so much.
It's very nice to be here this afternoon. Thank you. I am talking on a slightly different angle to everyone else who's presented today. I'm talking about applications of remote sensing data. And so I'm specifically focusing on applications of HCAS. And so as Roozbeh said, HCAS is a partnership between CSIRO and the Australian government, and the aim being to develop a nationally consistent approach to monitor Australia's ecosystems at high resolution and frequency. The development of HCAS was motivated by knowledge that the degradation and loss of Australia's ecosystems are driving declines in biodiversity and ecosystem services. Australia is not alone in this. Recent estimates suggest that nearly 60% of the world's terrestrial areas are under moderate or intense human pressure, less than 25% relatively free of direct anthropogenic disturbances. And so responding to this situation requires information on where and to what degree ecosystem condition has changed. And so today I'm going to highlight 4 examples of how considering the status and trends in ecosystem condition, specifically HCAS, is being used in Australia to support reporting and the development of strategies and plans. So the first application is the National Connectivity Index. This was a collaboration between CSIRO and the New South Wales state government, who are acting on behalf of the Australian government. Connectivity is an emergent property of habitat quality, amount and arrangement, and the publication of HCAS provided a key opportunity to update and revise the index that was already existing in a much more simplified form. So the revised index, which was developed by people working in the New South Wales government, Michael Drielsma and Simon Ferrier, measures the amount of connected habitat within a biological neighbourhood. And it does this by considering how ecosystem condition facilitates or impedes biotic movement and dispersal. And it employs a multi-scale analysis to represent connectivity for a broad range of taxa. So here it's trying to think about connectivity from local home range movements through to large interregional migrations. And so in being derived from HCAS, the National Connectivity Index describes the interaction between a specific location's condition, its site-based condition, and the context within which that location exists. So the index is reported as a percent of connectivity that's remaining relative to a pre-European baseline. So approximately 1750. So the most recent estimate puts the amount of connectivity remaining at around 42%. And so this is based on the long-term average that comes out of HCAS, so from 1988 to 22. And this example just shows how we can summarise the index by Australia's bioregions. Here we're using IBRA bioregions. And this actually, this figure is using an earlier version of HCAS. But what this is demonstrating is how the data can provide informative high-level summaries that can be used by decision makers and policy managers. And it's showing between region variation. These are the averages for each bioregion, which are on the map, and also within region variation. And so here we can just demonstrate the internal variability, and I've picked 4 regions to look at here with quite distinct connectivity profiles. So the highest scores are locations that are well connected to high quality and quantity habitat, and the lowest scores typical of your extensively modified agricultural regions. Intermediate scores can result from multiple ways. So, for example, they might be small patches of high-quality habitat that are situated in a modified matrix, or they could be large swathes of medium condition habitat. So the HCAS and the National Connectivity Index have been adopted by the Australian Government for annual reporting on activities supporting environmental outcomes. So this is measured as the measure EN01. The target here of this measure is to maintain or improve the trajectories of these scores. So the national average of the HCAS scores, that's what's shown in the left-hand panel, and the national average of the NCI scores are shown on the right. And these are measured, and this target is relative to a 2018 baseline. So what we can see is that at a national level, the HCAS and NCI scores have remained relatively stable over the past 5 years. However, the national, which is, it's good, achieving the target, but when we can drill down into this further and support this index by looking at subnational analyses and narratives. And here, summarising HCAS, again using IBRA regions, we can see that on the left, this is the state of the system. So this is the HCAS long-term average, and this is the average for each bioregion. So we can see a more nuanced understanding than the headline indicator provides. On the right, however, we have the trend in ecosystem condition over this period. And so this trend is applied to the average of the annual epoch. So these are the 3-year rolling averages that Roozbeh talked about. And the benefit of the trend is that it can highlight where changes in condition have occurred, their magnitude, and also statistical significance, which are the yellow points in some of the bioregions. And the Australian government uses this information to support the development of programs and strategies and plans that will support nature positive outcomes. HCAS is also featured in the most recent Australian State of the Environment report, which is a comprehensive assessment of the environment based on the best available evidence. This is produced every 5 years. HCAS was a key data underpinning the land chapter as it enabled reporting across all of Australia's ecosystems. In the report, it was used in 3 ways, really, to classify the continent into 3 land use intensity zones, just understanding those broad trends in how ecosystem condition is distributed. These were based on average condition. To assess how condition varies within and between ecosystem or vegetation types, and to assess the extent of modification of a vegetation types. And this is what's shown in the figure on the right there. Here the colours represent 5 condition classes that are related to increasing levels of modification. And some people might recognise the terms that we've used on those classes, which are drawn from the vast narrative framework, Vegetation, Asset States and Transitions, developed by Richard Thackway. And the size of the bars here indicates the percentage of the pre-European area that was taken up by that vegetation type. So it's a nice succinct way to describe how the variation of the continent sits and by these different types, and highlight different vegetation types that might need focusing on. The 4th example comes from work undertaken in the regional ecosystem accounting pilot projects during 2022-23. And here HCAS was being used in experimental ecosystem condition accounts. These accounts were developed to align with the United Nations Ecosystem Accounting Framework, and this framework provides a standard to integrate environmental and economic measures. And this is really to be used as an aid for reporting and decision making. For the accounts, HCAS was combined with mapping of ecosystem types and states. And these ecosystem types and states were based on conceptual models developed in conjunction with regional experts and under a framework called the Australian Ecosystem Models Framework that is developed by my CSIRO colleagues. So this figure here is just showing 2 ecosystem types for the Flinders Norman Gilbert region, which is one of 3 case study regions. The solid lines show the average annual condition scores across the time series, and the dotted lines indicate the trend in condition, which this type of presentation can be used by decision makers at a local or more regional level to understand what's going on in their system. As ecosystems are dynamic, however, measures of condition can and will fluctuate from year to year, and the trend potentially provides more ecologically meaningful information in that sense. This far right-hand panel, I just wanted to show because here it's showing the extent of the different ecosystem states, and this is highlighting how linking remotely sense-based ecosystem condition data with conceptual models that might be derived from expert knowledge can provide information or hypotheses about the mechanisms driving changes in condition. So, for example, in the bottom class on the lower panel, which is a modified bare soil state, if there was a large increase in this state, you would expect a consequent drop in ecosystem condition. The HCAS team has also been developing an approach to summarise temporal trends in a spatially explicit way. So here in this map, the red indicates decreasing condition across the time series, with white being no statistically significant change being detected. The spatial trend analysis can report not only the direction and magnitude of change, but also identify places with more or less change for further investigation. And the graph on the right is just being showing to demonstrate how the data can be aggregated by any spatial extent to provide the most relevant summaries for managers or decision makers. Almost done. So this last example shows the biodiversity habitat index. So this index is a component indicator in the Kunming-Montreal Global Biodiversity Framework. And to calculate this metric, we combined ecosystem condition data, HCAS, with spatial models of biodiversity turnover and richness. The BHI estimates the number of originally occurring species that are expected to persist in the long term anywhere across their range, but given the current patterns of ecosystem condition. And as the figure shows, we use the BHI as an indicator in biodiversity accounts as part of the UN Ecosystem Accounting Framework. And finally, this is just for interest, the Australian government's recently developed a public web map viewer for HCAS. And so this can be used to explore the data, and the little QR code in the corner there should send you to the page. And just like to acknowledge a whole lot of people that made all this work possible, and thank you.
Thank you, Dr. Kate and Dr. Roozbeh, for this awesome presentation with some interesting graphics. Okay, there is one question already asked in the QA box. Is very interesting question. Can you briefly explain the difference between HCAS and HCRAS? I know what is HCRAS, so if any of you, Dr. Roozbeh, Dr. Kate, can again maybe just a recap of what is HCAS, then I can add my answers to HCRAS.
Can you explain what HCRAS is, so I can see the differences?
HCRAS is a software, it's a modeling software which is mainly used for flood modeling. simulations is actually used for simulating the hydraulics of water bodies in rivers and channels that developed by the US Army, I think, Hydrological Engineering Department. Yep.
So essentially apple and oranges.
Yes.
So HCAS, as I explained, is a software and system to assess habitat condition across the landscape, in this case Australia, which is quite different. Yep.
Thanks, Roozbeh. I think, sorry, I forgot to mention the question has been asked by Rehan Jamil. I think you have got your answer, Rehan. Is there any other questions you can put in the question answer box or in the chat window as well, if you like?
Sorry, may I ask question? Sorry. For habitat condition, so that's considering the ecosystem, is the model considering the different ecosystem when assessing the condition and giving the metrics of analysis? Like maybe in the agriculture landscape is different, or in the forest area is different.
Yeah, exactly.
So
yeah, so in the assessing condition of any location, we are not selecting the reference sites or the training site from all over Australia. That will be limited to proximity first, and then limited to the landscape that they are more similar to the target point. So at target points, select the points that are based on predicted remote sensing variables, which are coming from 40, 50 environmental variables, including the temperature, snow cover, soil, all sort of information of the ecosystem characteristics are used to predict the remote sensing variables, and that is used to filter the data and not selecting. So if you are selecting something in like a temperate forest, relatively in a homogeneous environment, the point that are selected for that specific point would be at this stage, for example, would be within 100, 200 kilometers within that similar environment. So, yep, essentially the algorithm take to account for that each environment should be different from the other one. Like a natural grassland would be different from a rainforest. So the rainforest samples that it's comparing to, it will be selected based on the similar environment type of thing. If that answers your question.
yeah, thank you.
All right.
Thanks, Roozbeh. There is a question from Heidi Van Deventer. Is HCAS also used for monitoring wetlands?
Good question. Since using Landsat, we have a team, like a sub-team in HCAS that are working on riparian areas. So it uses freshwater ecosystems. We have been using more samples and included variables to take to account for freshwater ecosystems and including wetlands. But at the moment we are working on it and we are trying to improve the HCAS condition assessment for wetlands as well. But at the moment it is one metric that is using, but we have used things to improve the condition for wetlands. So they will be also included into the condition assessment.
Thanks, Roozbeh. There is a question from Yang Cheng. I don't understand. He asked, just wonder if there is any researches conducted on which bioregion reacted better for vegetation recovery after the wildfire.
I'm not aware of that. Do you?
Yeah, maybe.
No. So I don't think that has been assessed. So it would be possible to use the data to look at
Exactly.
At the change in condition, but yes, we haven't done that as yet.
Thanks, That's great. I have a quick question, which is may not directly related to the work that you have presented, but I'm interested to know the interactive diagnostic tools that you present, Roozbeh. Is it available for people outside CSIRO?
Unfortunately not. I need to, at the moment it's local, I need to put it on the Shiny server for CSIRO, so you might be able to have a look at it. But if you like to have a look at the code, it's a Shiny application. I'm happy to share that side of the code, but that would only be working with the HCAS data and HCAS assessment. But if you are just interested in software development, I can share the code with you. But inside CSIRO, not outside CSIRO, unfortunately, at this stage.
And also, like the new version 3 is not already available.
I think the version 3 is already online, and version 3.3 that I developed last week that extend to 2024 is already published in the app. The software is not too software involved to process these. A HCAS that it used to be a C++ software. I developed it as a RCCP in C++ and R, and then a workflow that automate things on CSIRO systems. But that is also at the moment is limited to CSIRO, but the product are available.
Okay, thanks very much. Is there any other question for Dr. Roozbeh and Dr. Kate? I cannot see any.
Sorry, it's getting one more. Just quickly. Is this like habitat condition assessment would be useful for fire application? For example, if you have the assessment of like habitat condition like before fire, and then what happened during the fire season, and then after that. So at least you can get some insight of that. And then maybe for future prediction of the fire risk or kind of thing, if that information could be useful, and what kind of information can be provided in this case?
Certainly you can check the degradation of the condition after like a severe fire and see what's going on there, but it's predicting for the future. I'm not 100% sure, because the HCAS, although it relates to vegetation, it doesn't necessarily means that a vegetation cover and the potential of fire. So one of the key component in fire is fuel. So fuel, air, and ignition. So that fuel side that it's need to get some indication from HCAS is not 100% always like there is no very strong relationship between the, like, for example, biomass and HCAS, because, for example, in middle of Australia, in some areas that is very low grassland, not much of biomass, if they are in an intact condition, hasn't changed comparative to the other reference site in the similar environment and condition, they get a HCAS score of 1. And in a temperate forest with a lot of fuel that is in the good condition as well, untouched, also get a value of 1 for a good condition, or vice versa, bad value or value of 0 or close to 0. So that doesn't directly translate to fuel, and it might not be very useful for fire, or some, like I could imagine, for example, for like species distribution modeling or something like that. Where is the condition for this koala or possum is good across the landscape, is somewhere is degraded and there is a parking lot instead of a forest, definitely cannot find a koala living there. So, but for fuel, it would be a different story. I doubt that you could directly get some sense of fuel from HCAS product.
I think there's one other aspect, if I can add in, which is that part of the idea of HCAS is that it the reference state is a dynamic reference state. So if part of your natural cycle of your vegetation actually involves being burnt on, say, a 3-yearly basis, then that would be captured in, you would hope that your reference site data would be capturing that imagery, and so be calling that actually a natural image. So if there are, you know, very large severe fires that are out of, you know, unprecedented, to use, you know, modern terminology, then we'd hope to be able to pick them up and pick them up well. And I think that we've done a small case study looking at the impacts of some of the 2019-2020 fires on the Gondwanan rainforests in northern New South Wales. And so the impact there was picked up well. But yes, we hopefully wouldn't always want to be getting a decrease in condition for an ecosystem that burns quite frequently. So, yeah.
Okay, thanks, Roozbeh. I have a quick question. I think I have seen a slide when Kate, you were presenting that there is a lack of training samples in Tasmania region, and if I'm not wrong, in the Gippsland Desert region. There is like a thatched area. You said that there are very less samples. So is it like because no satellite image covering those area? Because I can understand that Gippsland Desert might not have that much of biomass. It's a desert area, and the Tasmania as well. In your image, I've observed. So is there a reason like there is a less samples from those regions?
Which one, mine or Kate's
No,
presentation?
Kate's presentation. It's a hashed.
Yeah, yes, I think that's so, Roozbeh, I think that's the image of the trend over time. And so Tasmania, I believe, was not the training samples, but cloud cover, if that's right, Roozbeh.
Yeah, that's true. So the quality, so we assessed that the quality of the input data was not sufficient to drive the trend. For that case, we excluded. So we have product out of it, but we because the cloud coverage is an issue over there, we didn't want to drive insight out of it, and it's not completely reliable.
Okay, thank you. I think there's no other questions, so I can hand it over to Mladen.
Thank you, Dr. Sarker. Thank you very much. Yes, I also see that there are no more questions. So at this point, we can start to wrap up this webinar. And I don't know if Dr. Arnick has something to add in the end, like some closing statement or something like that.
Not too much. I just want to again thank you all of our speakers to kindly accepted our invitation to join and share the great expertise and experience to us, and also all the participants for joining. Hopefully that you find this insightful webinar. We are open to further question to answer through emails or website, the webinar website, and also opportunities for collaboration in the future as well. Thank you so much.
Thank you very much. Thank you very much. A special thank to our chairs and speakers for sharing their expertise and work, and thank you all in the audience for your questions and for your active participation. We have a lot of questions today. I think this is the webinar with most questions so far that I hosted. So we hope that presentation have sparked new ideas, inspired maybe some new collaboration, and definitely provided a clearer view on how remote sensing and artificial intelligence could shape the future of vegetation monitoring. Before we close, again, just a few reminders that the recording of the webinar will be made available soon. And if you're interested to contribute to this field, consider submitting your work to the special issue that we shared in the chat, or please feel free to reach out to the editorial team. Please feel to reach out to our speakers, of course, and our chairs if you have any more questions. And of course, stay tuned for more events related to this webinar series. Until next time, thank you again for being the part of today's discussion, and take care and see you in the future sessions.